are the intermolecular force available to matter? We're going to concentrate on 3 intermolecular force. Okay, there's more out there, but we're going to concentrate just on 3, and this lab just deals with 3. The 3 are dipole, dipole type of intermolecular force. The second one is called Londinium. Intermolecular force. And the last one is hydrogen bonding. Intermolecular force. Okay? Those are the 3 that we're going to concentrate on. Dipole-dipole is going to be available only for polar chemicals. Only polar chemicals will have dipole-dipole intermolecular force. Okay. The greater the polarity of the chemical, the higher the intermolecular force for that particular chemical will be. Okay? The greater the polarity, if it's a more polar chemical, then if it has the same molecular weight, because molecular weight also plays the same an important role. But if you have 2 chemicals, like for example CO and nitrogen, this has a molecular weight of 28, this has a molecular weight of 28, but this has is more polar. Carbon monoxide is more polar than dinitrogen. This has a higher boiling point. Okay, because of dipole-dipole intermolecular force. So when you're choosing from a list of chemicals and you're trying to figure out what type of intermolecular forces these particular chemicals possess, you have to know whether it's polar or non-polar. Because if it's polar, then you want to check off dipole-dipole interaction. Okay, I think that's a Prelab question.
Do you have dipole-dipole forces and hydrogen bonding?
Yes. Okay. In fact, if you have hydrogen bonding, you also have dipole-dipole. Okay. Dipole-dipole is a criteria for hydrogen bonding because hydrogen bondings are a sort of polar chemicals. So polar chemicals will have dipole-dipole interaction. Intermolecular forces that has London dispersion force will be polar chemicals as well as non-polar chemicals. So you can see that polar chemicals will have London dispersion force as well as dipole-dipole, but non-polar chemicals can only have London dispersion force. That's the only force available to those particular chemicals. And how do you know it's non-polar? Because the chemical is symmetric and the electrons are evenly distributed through the entire chemical. Okay? I'll give you an example. Let's consider CH4, okay, N2, O2, and xenon. All of these are non-polar. Okay, because CH4 is tetrahedral and the chemical structure is a symmetric structure in which its electrons are evenly distributed throughout. N2 is non-polar because there's 2 atoms that are bonded together by a triple bond. Again, the electrons are evenly distributed throughout. Same with oxygen. Non-polar, electrons are evenly distributed, and xenon, you can't get any more non-polar than noble gases. These things only have 1 element, and it's got a full octet in its surroundings, and so all of these are non-polar. The strength of its intermolecular force has to do with the size. The bigger the particular element, the further the electrons are from the nucleus. Let's consider xenon, argon, and helium. You guys know that helium is the smallest among these noble gas? And so the electrons are very close in. Argon, on the other hand, is in the middle, and so the electrons are sort of intermediate in terms of xenon and helium. What happens for nonpolar chemicals is that the electrons, let's say I have several xenons here, the electrons are whizzing in their orbital, and every once in a while, especially at low temperature, the electrons are going to bunch up in one area. The electrons just sort of migrate to one area, and so this one area now becomes partially negative. It's got an overload of negative electrons. So if this side becomes overloaded with electrons, it's got partially negative. The other side of this xenon is partially positive. You now have a dipole situation. Even though it's non-polar, you've got an instantaneous dipole that results from electrons shifting. What happens to the neighbor is that it sees this buildup of electrons here, and so the next xenon atom will have its electron respond accordingly. The electrons are going to be repelled by this buildup of negative charge, and so this side becomes partially negative, and the closest side to its neighbor becomes partially positive, and you have this attraction right there. That attraction between two nonpolar chemicals, or even between polar chemicals, as long as the electrons are causing it, is what we call London dispersion force, LDF. Okay? The bigger the chemical, the more this is likely to happen. The smaller the chemical, the electrons are not influenced as much. So xenon will have a boiling point of about 166 Kelvin, whereas helium will have a boiling point of about 4.7 Kelvin. It's much lower because the London dispersion force is weaker in helium than it is in xenon. It's a bigger chemical. Okay? So when you have a list of CH4, SiH4, GeH4, and the geometry is the same, the only difference is that one chemical is larger than the other, you can say that the highest boiling point will be GeH4, the lowest boiling point will be CH4. The highest melting point will be GeH4, the lowest melting point will be CH4. The highest viscosity would be GeH4, the lowest viscosity would be CH4. The highest vapor pressure will be CH4, the lowest vapor pressure will be GeH4. It's just the opposite with vapor pressure. Okay? So remember that. Vapor pressure is the only one that's opposite to the trend. Question?
As far as the electrons swaying each way,
that just randomly happens. Yeah. It happens because you're at low temperature. That's just the nature of the beast. The electrons will eventually migrate to one side, and it's that instant that causes this ripple effect. Okay?
Any atom.
Any atom. Okay? So, right?
So does that mean is the dispersion force only for the noble gases, or it's for like...
It's for all chemicals, but because noble gases, that's the only force available to it, that's the only force it can have, that's the only factor that we can look at that determines its boiling point or melting point or things like that. Okay? Whereas if you have a chemical that's polar like NH3 and PH3, not only does it have London dispersion force, it also has dipole-dipole interaction. So you have to look at those two factors as well as the size. Okay? So it's a little bit more complicated. Now, it just so happens that if you take the boiling points of these series right here, H2TE, H2SE, H2S, the boiling point of that's about 10 degrees Celsius. The boiling point of that is about minus 50, minus 25 degrees, somewhere in that order. And the boiling point of that is about minus 50 degrees Celsius. You would expect water to have a boiling point of about minus 100 degrees Celsius if we just look at the size. Okay? The fact that water does not have a negative 100 degrees Celsius but have a boiling point of positive 100 degrees Celsius tells you there's another type of intermolecular force in play here. And that other type of intermolecular force is hydrogen bonding. Okay? Hydrogen bonding is the third and probably the most important in terms of life as we know it. How does hydrogen bonding occur? It occurs because you've got hydrogen, which is the most simple element, bonded to an element that is really dipole. It wants electrons. If you have hydrogen attached to an element X that is hoarding electrons, that is stingy for electrons, then you know that hydrogen with its one proton and one electron is going to be exposed. Let me try and diagram this. You've got hydrogen, it's got one proton here, and it's got one electron here, and that electron is being shared by this particular element. Let's say that this element is oxygen or fluorine, for example. The fluorine is going to cause that electron to be attracted to the nucleus of the fluorine atom. And so it's not going to be in between the hydrogen atom and the fluorine atom. It's going to be distorted over towards the fluorine atom. So you can see that the electron is pretty much drawn away from that proton when it's bonded to an electronegative element. So the criteria for hydrogen bonding is that hydrogen has to be bonded to electronegative element like nitrogen, oxygen, fluorine, sometimes chlorine, because chlorine and nitrogen have the same electronegativity, 3.0. But it's a bigger atom, so it's not as efficient. But what happens is that, you see how this proton now is exposed? This proton is exposed because the electron is being distracted away from it. Well, you've got another fluorine atom nearby, and that fluorine atom has a lot of electrons in its area. That proton is going to be attracted to that sea of electrons near the fluorine. And so that attraction right there is what we call hydrogen bonding. It's not a true bond. It's an attractive force between charges, but it's so strong we give it a special name called hydrogen bonding. And that's why water has a higher boiling point than expected. It's the hydrogen bonding mechanism that causes water to have a boiling point of 100 degrees rather than a negative 100 degrees.